Cool. Thank you for coming, everyone, and sticking with us. I'm here today to talk about password hash cracking. Just a brief bit about me. I'm Sam Shute. You may also know me as Goldstein. I'm a principal technical consultant at Quantum Security. So that's doing things like network pen testing, web app pen testing, host configuration reviews, Wi-Fi pen testing, red teaming, stuff like that. My sort of general interests involve network pen testing, physical security, and electronics. I also do a bit of 3D printing and have done some research on that sort of thing in the past as well. But today we're here to talk about some stuff to do with hashing. So first I want to do a bit of an explanation of the difference between hashing and encryption. So both encryption and hashing take in our plain text values that we want to keep kind of secret and convert them into an unrecognizable value. The difference at a high level depends on what we want to use that value for. If we ever need to see that original value again in future, then we need to encrypt it so that we can decrypt it. So it's a sort of a reversible function. Whereas for hashing, if we never need to see it again, then we can use a one-way function. You can think of it kind of like for encryption, you'd want to send a secret message to someone. You want to be able to be sure that they can actually read it on the other end, because if they can't, it's kind of useless. And with hashing, it would be for something like validating passwords, like we're going to talk about today, where you want to authenticate someone, so it doesn't actually matter what the value that they give you is, as long as we know that it matches what it's supposed to be. Oh, actually, there's a bit more to talk about there. Yeah, sorry. You can think of it kind of like making fruit juice. If we get a collection of fruits and put them into a blender, we get some juice out at the end. That's kind of like our one-way function, because you can't turn juice back into fruit. But if we put all the same fruits into the blender again, we should get the same juice out. And if we taste them, they should taste exactly the same. Cool. So now I want to do a bit of a brief talk through password requirements. You might be familiar with things like having a bike lock, where you have 3 or 4 little dials that have 0 to 9 on them. So in the case of having 3 dials, you have 1,000 different combinations from zeros up to 999. If you were to go through these and check one combination every 10 seconds, it would only take you 2 hours and 47 minutes to try every different combination on one of these bike locks. That's something to keep in mind as we go through the rest of this talk. Because when we change our password requirements to increase that number, it takes longer to do things. So if you were to have 4 rotors on your lock instead, it would take you much longer. Where we're doing this with passwords, you're not sitting there typing in one password at a time, trying them manually by hand, one every 10 seconds. Instead, you're trying to crack these automatically, like computationally, through GPUs. The NZISM sets out some password requirements for government agencies. This is fairly common sort of password requirements that you'll see around everywhere. Is password lengths of being 10 with a mixture of characters, or 16 with no complexity requirements. You'll notice some of the slides have gold stars on them. If you keep a note of those ones, there'll be something at the end for that. So where we're talking about password requirements, those complexity requirements that we had before, where you had lowercase letters, uppercase letters, digits, and special characters. This is based on a standard US keyboard. You'll have 95 different characters that are involved. So previously, when we had a look at that bike lock before, there was only 10 different values that you could have between 0 and 9. Whereas for a password, each character can be 95 different values, and so that massively increases the complexity. You can think of it kind of like this, using these sort of mathematical displays of what they are. For that bike lock that we looked at the start, you'd have 10 to the power of 3, where you have 10 characters to the power of how long the password is. So for something like old password requirements, or you might still have applications like your password for your bank that only require you to have 8 characters, that's not great, but it's still 95 different instances to the power of 8, which is the length of that password. That's what that actually looks like in terms of what that number means. So it is still kind of heaps, but it's not heaps, as we'll see later on. This number is 6,634,204,300,000,000. So that sounds like a lot to me, but in reality it's kind of not. You'll see the E plus on the end. That's kind of how many digits back you need to move that full stop that's there, that decimal point. So by the time you get down to 10 with no complexity, or 16 with no complexity, you're ending up with huge numbers. One thing that you can note here is the difference between 8 characters with no complexity and 8 characters with 3 complexity. I won't bore you with the maths of how you go about doing that, but you'll see that it's actually less than half. So by enforcing a complexity requirement, you actually reduce the number of possible passwords that someone can have in half, which can massively decrease the hash cracking time later on. We'll also briefly cover over where you can collect passwords from. This is a picture of the first hash cracking rig that we built at Quantum that had 4 2080 Ti's in it. So we've moved on a little bit since then in terms of what we can do. But some places that you can get passwords include Responder. So if you're on a network somewhere and you set up Responder, you can trick people into thinking that you're a network share or some other things, and they'll just send you password hashes, which is great, and then we can take those offline and crack them. Sometimes during an engagement, you'll actually breach a host or a domain controller, and you'll get dumps of SAM hashes or LSAS or NTDS. These tend to be in NTLM format. If you had only 8 characters, like we talked about previously, using modern GPUs like the RTX 3090s that are available at the moment, you could crack those in under 2 hours. So 8 characters is obviously not sufficient. One thing to keep in mind is that you don't always have to crack the hashes though. Even though this is, the point of this talk is to crack hashes, there are other techniques that you can use that don't require you to do that, and you can just use those hashes straight away. You can also get passwords from database dumps, so sometimes you'll break into an application and you'll be able to dump out the database. Different algorithms depending on how the person who built the database is storing their passwords. You can get those, like I was saying, on the job. There's also both private and public dumps available online, depending on whether you just want to take what's available or buy something. These are often really useful because people tend to reuse account passwords, as we know. Which is kind of the value in cracking that hash back into a clear text value, is then we can go and use it to try and log into everything else. Sometimes you'll also come across other sources of passwords where the big four will just leave password dumps on network shares for you, and you can take these offline, and that's fantastic on the job. So now we'll get into how to actually do hash cracking. So we've collected some hashes. What do we do with them? We can use dictionary attacks, brute force attacks, masks, or rules. These are kind of the broad 4 categories that most attacks fit into. Dictionary attacks, we're just trying the most common passwords. There's lots of password lists that are available online that you can use, from things like sec lists or CrackStation, that will give you the 1,000,000 most common passwords that you can go and try really quickly. Where we were talking before about using those by clocks, and you'd try 1 every 10 seconds, if you were to try this using a GPU, you're instead trying millions of passwords per second. So brute force attacks, you can see that this is kind of different, where you start with the first value, then you kind of just increment it by 1, and by 1, and by 1, and by 1, and you try every possible value. The difference between these is that this is sort of a very fast approach that works really well for getting most passwords, whereas if you have the time and computational ability, this will eventually get you every password. There are some tools available, so things like Hashcat that will let you do masked attacks instead. So where you generate those random passwords, or the brute force passwords like we were looking at before, instead of going through every single one, we can specify some constraints of what we want to do. So we only want to look at lowercase characters and we only want to look at numbers. So for example, if we know that this person has generated their password and we know that the first character is uppercase and then it's 7 lowercase characters, or 8 lowercase characters, and then a number on the end, because that's the organization's password requirements, then we can just use these masks where you select whatever the value is that you want for each character in sequence, and then it'll only generate passwords that meet those requirements. The S character there is the special character set. That is I think it was the 33 characters that we looked at before that make up the part of the 95, the others being lowercase, uppercase, and numbers. So you can actually see that in the A set. So the A set is made up of lowercase, uppercase, decimals, and specials. Cool. Rules is kind of a variation of the dictionary attack that we looked at before. So you take in a pre-known password list and then you apply rules to it to change it. So say we've run our dictionary attack and it's only taken us 5 minutes to run it, but we've only got 10% of the passwords that we have and we want to get more. Instead, what we can do is we can change all characters to uppercase, or make sure we capitalize the first character of every password, or we can replace every instance of A with the @ symbol. So we can go through things like that that'll sort of provide those common transforms on passwords that can make old password lists useful again, such as appending 2021 to every single password, because Service Desk loves adding the year on the end of the password. This is kind of a bit of a jump from what we were just talking about, but it's a way of adding extra protection. So I guess this is kind of one for any developers in the room. You can salt passwords to make cracking them more difficult. The first line here is, so we're going to apply the SHA-2 hashing algorithm to the password 12. And it'll end up with that hash. Every time we apply that hashing algorithm to that password, we'll get the same value out. That's really useful for when we want to validate who a person is, because they give us the password. Every time we hash it, we get the same value back. We know it's still them. That becomes a bit of a problem when we have millions of users and a lot of these users will be using the same password. Every time we hash those passwords, we're going to get the same value out. That means that if anyone ever dumps the database and they see a whole lot of hashes that are exactly the same, we know that that's probably a priority hash that we want to go and crack really quickly, because it'll give us access to a whole ton of accounts. One way to get around that is to apply a value called a salt to the password. So that just adds an additional string, which is randomized for each password that's stored, to modify the value that we get out of the hash at the end. So you can see that at the bottom there. This is the way that hashes get stored in the Etsy shadow file for the SHA-256 algorithm. It says the $5 being the SHA-256 hash algorithm, another $ as a separator. Then we've got that value in there where it's SDUFHIU, blah, 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 blah. And then another $ as a separator. When the user provides their password, we can go and grab that chunk out again, concatenate the two together, apply the algorithm that's defined, and we should get that hash out. So we can see that that's different for these two here, where we've applied two different salts to the same password, and we get two very different hashes out at the end. So now you're saying, okay, cool, Sam, I've got some hashes and I know theoretically kind of how to do this, but what do we do? So there's a few ways that you can go about practically doing this. You can build your own cracking rig. You can build multiple cracking rigs and sort of do a distributed method of cracking them. You can use cloud-hosted hash cracking or community-distributed hash cracking. The first one of those that we'll cover is building a cracking rig. So this was one that I built a few months ago, just sitting on the carpet at home, which is great for electrical components. The first thing that we need to do is get all the sort of base components together. So that's things like a motherboard, CPU, RAM, all that kind of stuff. For the most part, the RAM and the CPU that you get don't really matter as long as it's enough to run whatever operating system you're wanting. There are some constraints involved in certain CPUs where they only allow you to have certain numbers of PCIe lines for use of devices like graphics cards, but that would be kind of a whole talk on its own, so I'll leave that out for now. And then two other sort of things that you need besides the GPUs are PCIe risers and splitters. You don't have to have these, but they make it way easier. So risers are these devices here that sort of remove the physical constraints of motherboards. If you've seen a motherboard before, you know those lines that you put the graphics cards into are way too close together, and it means that you can only really fit like 2 or at the most 3 graphics cards on a single motherboard. So these are kind of made to fix that problem. So you put the tiny piece in the middle into the motherboard, and then you connect the cable onto the riser, and then you can put the riser wherever you want connected to the graphics card. There's a URL at the bottom there that you can go to later that has a cool sort of history of how we got to this point from where we are today, and I'll cover over that really briefly. So the next, all of the images, or most of the images from what I'm about to talk about have come from that URL. These were sort of the very first version of risers that existed, where you sort of cut the bottom off of another PCIe-based device and cut the bottom off of a PCIe slot and then soldered ribbon cable between the two of them. This obviously had a lot of problems and was a pretty hacky approach to getting something to work. This was kind of driven by the massive rise in cryptocurrencies and the need to be able to put more GPUs per motherboard together to mine cryptocurrencies faster. Lots of these thick ribbon cables like this would obviously have a pretty severe impact on airflow within wherever you've got the cards though, so that's obviously a really big problem for something like GPUs that generate a lot of heat. So that sort of led to this. For most mining and hash cracking, we don't actually care about having a ×16 line, which is the really long slot that we've got at the top. We physically have to have that for the graphics cards, but in terms of throughput, we only really need like a 1 times PCIe connection. So you can do that with having the smaller bit at the bottom, just soldered in exactly like it was before. This kind of migrated to having thinner cables, which meant better airflow, but still pretty hacky approach. It also meant that because you have way more of those slots that have small PCIe slots on a motherboard, you can have more GPUs. So you're now looking at like 5, 6 kind of GPUs per motherboard. But as you have that many GPUs, they start to have to be spaced further apart, just because they are physically large devices, as well as generating quite a lot of heat. So that causes some problems with those cables becoming too long, as well as the motherboards not having enough 12-volt power supply to send power up those lines. So what ended up happening next was you'd separately power each of the GPUs over a Molex connection like that. This is one of those things where it was also a safety hazard, because you'd end up with motherboards being set on fire from trying to put too much power through a single line. That was where we sort of moved into the more modern age of GPU risers. This looks very similar to the picture that I showed you before, but it's actually quite different. This one only has 3 capacitors on it. It doesn't have any power like voltage regulators or anything like that on it. This was kind of the first thing that came out as the modern age. So these devices have the little chunk that clips into the board like I showed you before, a USB cable that goes between that piece and the board. The boards don't actually use the USB protocol, they purely use the USB cables because they're really cheap and they have the right number of wires in them. So they're just readily available. As well as being, if you need to buy longer ones or shorter ones, you can do that at a shop down the road rather than having to have it custom made. Then we went through kind of a few variations over the ages of these boards becoming better and better and better. So adding things like I was talking about before, like voltage stabilization and just sort of general improvements. You can see this was the change between, I think it was version 3, version 4, and version 5. There wasn't really huge noticeable changes beyond like stabilization and voltage. Then we moved into version 6, which was the most common version for several years. These ones introduced 6-pin PCIe as a much more reliable power method than using Molex like we had before. They also introduced more capacitors, analog stabilization, voltage regulation, things like that just made it that the cards weren't going to disconnect all the time, which was a massive pain when you're right in the middle of cracking some hashes or doing some crypto mining and everything just stops working for unknown reasons. And then you kind of get to where we are today. So this is a version 10 riser. This is kind of the standard at the moment. You have twice as many capacitors, so they've got redundancy for that. They've got metal shielding, and the PCIe slots are like soldered into the board more strongly, so they support a lot more weight. You've got a whole myriad of different connectors that you can use. They now come with 6-pin just on different angles in case you want to mount them at different angles. LEDs, some of them come with little temperature displays to tell you what temperature things are running at, which is kind of cool. So now we actually want to build something. We also need power supplies. These cards consume a huge amount of power. You're talking about ranging between maybe 50 watts for a really low-end card up to like 300 or 400 watts for your higher-end cards like 3090s. And if you're going to be running 8 of those in a single rig, you're now looking at, what is that, like 3.2 kilowatts. Most of the power supplies that you buy, if you've ever built a gaming PC, are kind of in that range of like 500 to 800 watts. Whereas when you start to move up into 1,000 watts, it becomes really expensive, and that's not even enough. So we'd need 4 of those just to power our rig, which obviously that doesn't work particularly well without having these multi-power supply switch connectors. So these are kind of like the high-end power supplies that I was talking about before. Most of these come with a whole bunch of PCIe power connectors, so that's these ones here. But you can see that even on these really high-end power supplies, you've only got 6 of them, and if each GPU uses 2 or 3 of those each, then yeah, you're going to have to spend a huge amount of money on these power supplies, as well as finding some way of linking them together, which is where these multi-PSU switch connectors came out. It lets you daisy chain power supplies together so that you can use different, like a whole bunch of power supplies to run one rig. It means that you can use cheapest power supplies or what's available. You can like daisy chain these connectors to run as many power supplies together as you want. You can also use server power supply breakout boards. So this kind of fixes that issue that we had before of only having 6 PCIe pins on a single power supply, 6 PCIe cables on a single power supply, sorry. So on this one here, you can see that we have 4 as a 4 as well as one in the middle. So we now have 17 cables, where previously we only had 6. That'll let you power a whole bunch more graphics cards, as well as you can buy server power supplies that come in much bigger ranges of power. The downside to those power supplies is they tend to be really, really noisy though, so it's probably not something that you want to have like sitting in your office while you're working or in your bedroom at home. I will kind of just briefly touch on this here, is that if you're dealing with anything that has large amounts of power going through it, you should be very, very careful. You should know the amount of power that the wires that you're using can handle. Where people were daisy chaining those Molex connectors and things in the past, they were running way too many of them that ended up in stuff catching fire. You don't want to be this guy. Things are not fine. Cool. The next piece being cooling. When we're dealing with that much power, you know those heaters that you have at home that you have out in winter that are like 2,000 watts, and you're like, oh, this is fantastic. This heats up the whole room. You're now dealing with something that's 1.5 times as powerful as that. So that's going to generate a huge amount of heat. So you need to find some way of cooling those. I'm not really sure why I've got overclocking here. It doesn't really fit with what I'm talking about. But yeah, you can overclock the cards to, or underpower them, so power limiting. So most graphics cards are sent out in a configuration that's useful for using them for things like gaming. Whereas when we're doing hash cracking, we don't actually need that much wattage running through it to get it to run the algorithms at the right speed. So you can cut the power usage often in half and only lose less than 1% of your computation rate. That obviously has a massive impact on your power bill as well. So where you're running a whole bunch of these together, like this. So this is my setup at home for doing hash cracking. It's got 21 GPUs, but that consumes a massive amount of power. If I was to run this at full power consumption, I'd probably burn my house down. So instead I only run it at like 50 to 60%, but I still get 99% of the hash cracking rate out of that. An individual one of those RTX 3090s could crack hashes at the rates kind of explained there. We were talking about trying one combination on a bike lock before, every 10 seconds. You're now looking at trying 65 billion passwords every second for MD5, up to like 121 billion passwords per second in original NTLM. The examples given below are for net NTLM v2, which is the hashes that you get out of responder that we were talking about at the start. I've used this as an example because it's the slowest hash rate of the ones listed there as sort of common hashing algorithms. From having 8 of those cards, you could crack an 8-character space in 46 hours, or it's actually less than 46 hours. So 8-character space is obviously not sufficient in terms of password length anymore. Yeah, if you were to have 32 of those, so not quite there yet, but 2/3 of the way, it would only take you 11 to 12 hours to crack that entire character space. Modern hash cracking, so we're going to talk about some things that are up and coming. You can run these in a distributed fashion, so sort of like the picture that I showed you before. You can set these all up to run as a cluster and then distribute the cracking that you're doing over several different rigs all connected together. That sort of helps you bypass those limitations of only having so many PCIe slots in a single computer. You can sort of cluster them and you essentially have unlimited now. We can also look at cloud hosting or community distributed hosting. So that was kind of what I just went through. Probably should have waited for this slide. The benefits of this is that, yeah, you keep everything on premise. That obviously has some pretty important security implications depending on who your client is and where you got these hashes from and what you're doing with them. If you're doing this as a business, cracking hashes, it's kind of irresponsible for you to put those up in the cloud. They should probably be dealt with on-prem so that you can secure those yourself. The downside being that the power and cooling requirements sort of massively increase as you scale, to the point now that my house is ridiculously hot and I have to leave the balcony open every day. So cloud hash cracking, AWS have these instances available that have a whole bunch of GPUs. They have each instance having 8 A100 GPUs. A100s are kind of comparable to an RTX 3090 in terms of their hash ability. If we look at that before, we've got 65 on MD5, 22 on SHA-1, NTLM is 120. Like we talked about before, NTLM was only 121 on an RTX 3090, so basically the same, and pretty much the same again for NTLM v2. They have these GPU instances built into things that they call ultra clusters, which are like 500 of these individual instances. You can't just buy that off the shelf. You have to apply to be able to use ultra clusters as a cluster. But if you were to use one of those ultra clusters to crack these hashes, you'd be able to do the entire 8-character space in 5.5 minutes, or the 10-character space in 35 days. That makes it kind of practical to crack these hashes. It's going to cost you an absolute fortune to do it, like we're going to talk about here, but it is possible. So for just renting one of these instances, not an ultra cluster, just one of those instances, you're looking at sort of between $16 and $45 per hour. That ranges depending on how much of this time that you're buying. To get that $16 per hour rate, you're looking at pre-buying 3 years worth of time to do this, which is going to cost you pretty big dollars. If you want a spot instance, yeah, you're looking at like $45, $46 an hour. Comparing that to building it yourself, so for this breakdown I've used $28,000 for GPUs. That would get you 8 RTX 3090s, $1,000 in power supplies, $800 in motherboard, CPU, RAM, and then $200 for risers and incidentals, because things always break. So your break-even time is only 27 days. So the whole point of doing things in the cloud was often sold as it's cheaper and I don't have to host it myself, and it's so much better. For something like this, if you only ever have to do it once, it probably is better that you do it that way, but it very quickly becomes cost-effective to do it yourself instead. Community distributed. So this is pretty theoretical at the moment. So Ethereum is switching from proof of work to proof of stake, which means that there's going to be a huge amount of computation power become available. Like, I mean, it's been in 6 months for the last 3 years, but like, hopefully in 6 months, all this computation should become available, which, yeah, you're looking at like petahashes per second instead of gigahashes like we were talking about before. If you were to use all of that hashing power to crack net NTLM v2 hashes, you could do the entire 10-character space in 30 minutes. And as kind of more of these services become available, so things like NiceHash, where they're making hashing power available to people for doing whatever they want with it, this kind of thing is going to become possible in future. So it'll be interesting to see where that goes. These are just sort of some other considerations because I've kind of gone over time. You can do mining as cost recovery, so when you're not on a job cracking hashes, you can just run this thing mining something like Ethereum or Ergo and sort of do cost recovery through that. You can tune them like I was talking about before. You can cut your power costs in half, as well as increasing performance by like up to 20-ish% depending on which GPUs you're using. You should keep in mind that lots of these risers and motherboards and things will throw PCIe errors all the time, and you'll probably run out of disk space, and that'll cause your rig to seem like it's crashed when it actually hasn't. So keep that in mind. And like we talked about before, is it actually a good idea to put client hashes into the cloud? This was the prize question that I was talking about before. So if you can have a look at the piece at the bottom there, it's got a mask that we could use for cracking hashes. Does anyone have an idea of why this would not be good for cracking NZISM passwords? I do have a prize available if someone knows why. Close. That's very close. Any more? No, so it can be 10 with complexity. So that in there has got 10 of the all characters. Yes. Yeah, so you'd end up trying to crack twice as many hashes as you should. That was where we looked at those numbers at the start, where you switch from 6 at the 15 to 3 at the 15. Yeah, you'd cut your cracking time in half if you were to actually optimize this instead. So the prize was one of the version 10 rises. So sort of some takeaways. Yeah, it's time to move to 16 characters as your minimum password length. As we kind of demonstrated, 10 characters is no longer sufficient. It's feasible to break that in a time frame that's actually going to be useful. Removing the complexity requirement has its pros and cons. From the sort of human element side of things, we know that people will pick the weakest passwords that we let them pick. If you set a 10-character limit, people will only pick passwords that are 10 characters. If you don't enforce complexity, they'll probably just use lowercase everything. But that does reduce your complexity pool, so those passwords that you do want to actually protect, like admin passwords, where those people are probably going to pick really strong passwords anyway, you're actually negatively impacting those passwords in some cases. If you want to crack a one-off password, yeah, cloud cracking could be a way to go for you. Yeah, I sort of can't stress that point enough that like putting client hashes into the clouds probably isn't a good idea. Yeah, take everything that you read online with a bit of salt, and you should probably be using some salt to store your passwords. Cool. Please come and talk to me about pen testing things or hash cracking later on. I'll be around at the pub. Yeah, thank you for your time, everybody.